Hello, thanks for joining me today. My name is Christian Steinmetz, and I want to talk about my project flowEQ, which is about using machine learning in MATLAB to build an intelligent EQ plugin. So first, just a little bit of background about myself. Currently, I'm a master's student at Universitat Pompeu Fabra in Barcelona, and I'm studying sound and music computing within the music technology group here. Before that, I did my undergraduate degree at Clemson University, and I did actually 2 bachelors there, one in electrical engineering and one focused on audio technology, so things like mixing, mastering, and live sound. And in addition, I've also worked a few different internships in audio-related things. Currently, I'm working at Dolby Labs as an intern here in Barcelona while I'm doing my master thesis, advised by Joan Seta. Before that, I also worked at Bose and Cirrus Logic. So my background is about, building tools for specifically audio engineers for mixing and mastering, things like that. So let's get right into it. So first, let's start a discussion about EQ and just go over some basic ideas and how this ties into the project and the big picture. So as I'm sure you're aware, one of the most popular tools that an audio engineer might use when making a mix or editing dialogue or things like that is the parametric equalizer, which is popular because it's a very powerful tool for shaping the timbre of different recordings. And the parametric EQ is interesting because it features powerful controls that gives the user a lot of ability to tweak and adjust things related to the timbre, the frequency content. And those 3 main controls are first the gain, which allows us to adjust, it's a boost, a cut, how much, things like this. The frequency, the center frequency, where is this filter going to impact frequencies across the spectrum? And the Q control or bandwidth, about how wide or narrow will this frequency adjustment be? And things can start to get very complex when you have more than one band. So here, we're just looking at one band, but as we increase the number of bands, 2 bands, 3 bands, five bands, now the complexity of the expressivity of this equalizer is very high, meaning there's tons of different ways you could set it right. So for the user, if they are, editing, let's say, a piano, and they recorded a piano, it has a certain sound. Now they want it to sound in their head, they want it to sound different. And, the mapping of figuring out which EQ parameters achieve this is quite difficult. And this is what audio engineers study. They're focused on learning, having the intuition immediately. How do I use this equalizer to achieve the sound I want? But for novice users, musicians or amateur recording engineers, this can be really tough. And the parametric EQ, is difficult to use for this reason. So with this additional control, you get complexity, as is often the case. So this is kind of one of the questions that flowEQ aims to answer. And now, what is flowEQ? So flowEQ aims to provide a simplified control of a parametric EQ by distilling the control of all of the 13 parameters of a 5-band parametric EQ into just 1, 2, or 3 controls that the user can select how many controls they want, And you can see just a demonstration here of the plugin where the user is adjusting one of the sliders here, and you'll see that the transfer function of the parametric EQ is changing in this kind of smooth fashion. And the idea here is that we want the user to use their ears to find the EQ setting they want instead of looking at things like cutoff frequency, gain, etc. And the idea is that it's kind of like a tone control, like the traditional tone control, bass, boost, treble, cut, things like this. But instead of having those simple, shelving filters, you actually have a full 5-band parametric EQ that the user can control with a very limited number of parameters and simply just tweak it till they get the sound they want. And we do this by using a machine learning method known as the disentangled variational autoencoder, or β-VAE. And we'll talk a little bit more about how that works and how it comes into play. So first, let's address the theory here. How are we going to think about this problem, and how can we potentially use machine learning to solve it? So first, we need to talk about this concept of something known as the autoencoder. And an autoencoder is comprised of 2 main functions. The first function is the encoder function. And in our case, the input are the 13 parameters of our parametric EQ. Then this function maps this input to a lower dimensional space in the middle, which we call the latent space. Then the second function is the decoder. And the decoder takes as input this compressed representation, and it tries to reconstruct the original parameters without having all the information there. And And we train this just by simply putting in an input and asking it to reconstruct itself. And you may say, well, this isn't very useful. And for example, here's how we plan to use it. Here is the decoder portion of the network here. And you'll see that there's this 2D latent space where we have an X and Y axis, basically. And that means that the encoder, what it's doing during training is mapping every single input to just 2 controls. And then the decoder has to take those 2 controls and try to map them back to all 13 controls as accurately as possible. And this forces this latent space to encode the information as efficiently as possible. And then what we want to do eventually is then have the user select a point in this 2D space. Then this will decode to a unique EQ configuration. Every point will. And if we train this well, this will provide us something useful because we can now use just 2 controls to control all 13 controls. And we go a little bit further because that's kind of just the formulation of what we would call a vanilla autoencoder. But we want to use something called a variational autoencoder, which essentially reformulates this encoder to be probabilistic. And I won't get into the math or the details of this, and you can check out this paper if you're interested in learning more. But it has some really nice features that are useful for us. The one is that it centers these projected points around the origin of this latent space. And this is nice because if we know now if we want to sample points, they're going to be basically centered around the origin. And it also means that similar samples, so EQ curves that are similar to each other, will be placed in the same area of this latent space. And this is, of course, what we want because we want to move around this latent space. And when we sample, we want them to be, some coherent movement that the user can understand. And it also means that the latent space will be densely populated. Again, what we want when the user is going to sample from it. And finally, we need to talk about this idea of disentanglement. And disentanglement is pretty simple. It just means that for every dimension within our latent space, that dimension encodes information about some high-level semantic property. So in this little graphic, I've shown that, for example, moving in the positive X direction means that you'll be getting an EQ that sounds more bright in comparison. And this is obviously really useful because now these controls can, if they're disentangled, now contain some sort of higher-level information. But the question is, how do we achieve this disentanglement? Because by default, this doesn't happen. And the answer is we adjust the loss function. And again, don't worry about the math here. You can check out the paper if you're interested in the details. But in this paper, they introduced something called the β-VAE to test out this disentanglement idea. Like, how can we enforce disentanglement while training the model? And it's very simple. They find that just by adding this beta in the loss function, which is just a scalar, just one value you can tune, what this does is actually weigh these 2 different loss terms differently. And changing this changes the representation we learn. And the simple takeaway is that a larger beta means greater disentanglement. And we'll see how that comes into play for our actual implementation here. So now let's talk about the actual model, how it's implemented, and how does this actually work. So the model architecture was designed to be purposefully simple. It's very small. It's by no means a deep neural network or anything like that. It's just a very simple neural network composed. You can see here the architecture, one dense layer for the encoder, and then a nonlinearity ReLU, and then we have the latent space, which is our mu and sigma. That's the distribution that's being predicted. Then we also have the decoder in the same way with a nonlinearity, and then an output layer that maps that down to 13 dimensions of the output, and then a sigmoid to make all of our outputs be bounded between 0 and 1. And there's a few reasons for having this super simple design. I mean, the first is that we want it to be really fast because this is going to be used in a real-time plugin. So we don't want the user to have to move a knob, and wait 3 seconds before they can hear something. So now in this formulation, they can move the sliders back and forth and there's no delay. And it also means that implementation in MATLAB is easier because a lot of the newer layers that you may want to use in a deep neural network aren't fully supported yet, because I actually had to implement this myself in MATLAB for it to work. And the final reason is that our data has low dimensionality. We're not dealing with images or raw audio here, so we can get away with a small network and it still works. And obviously for any machine learning project, we're going to need data to learn something useful, right? So in this case, we're using something called the SafeDB dataset, which is a really interesting dataset. And they basically, in this project, they built an equalizer. They gave it to a bunch of users and said, create EQ presets for your mixes that you're using, like on different sources, guitars, bass, etc. And what they found was that you could get all of these different EQ curves, right? And what I'm trying to do then is, what I'm saying is that these EQ curves are useful portions of the full search space of the EQ, because we know that there's many ways to configure it, but some are more used than others. So this data set gives us a way to kind of say, these are the points we care about. Now let the model learn how to structure them in a useful way. Now, some details about the training. So the first interesting thing is that we actually train 12 different models. And in each model, we adjust something a little bit to see how it affects the performance of the model. So we train with 3 different latent dimensions, 1D, 2D, 3D, and this controls how many parameters there are that the user controls. So in the 1D case, the user has one knob, and that controls all 13 knobs at the same time, and you see the pattern. And we also train with different values of beta. And this means we can observe how increasing beta changes the disentanglement. And we'll see more on that in a second. This is kind of a basic machine learning pipeline. You know, we use Keras, so all the training is done in Python. We save out the weights so that they could be loaded in MATLAB, atom optimizer, learning rate of 0.001. We train all the models for 200 epochs, and this whole process takes less than 2 hours on CPU, so very fast. Now, here is the latent space that I was talking about. So this is for one particular model and with a beta of 0. And what we do is we create a plot like this to kind of get an idea of the structure of the latent space of this particular model. And what we do is we take the XY coordinates of the latent space and we sample from them, and at each point we decode that and turn it into an EQ parameter. And you can see the transfer functions here. And now you'll see that as we change the beta, the EQ settings, the structure of this latent space changes. And basically what we're looking for is we want the best structure that lets users find the EQ setting they're looking for the fastest. So, like, see what happens here. And you can see up when we get to this point, now it's much more structured. It's very smooth as we move from one point to the other. And this is good. We want good continuity between the different parts of the latent space. And you can see actually what happens is if we go higher, now things become so much the same that if you look now, the x-axis has been completely removed from usefulness, in that if you look in the center and you move from left to right, there's no difference in the EQ. So now the x dimension has been completely forgotten. And this is what happens as you increase disentanglement too far, because now what it does is it's actually only using the y axis to encode information. So really what we would want is to end up using something like this one back here, and maybe this is the best. But in the plugin, we actually include all of these so you can listen to them. And now let's talk about the actual plugin implementation. How do we take the model and put it into MATLAB and make a plugin and actually make it, you know, have a real-time machine learning that we can use for some sort of application? So like I said, we use the MATLAB audio toolbox to do this. It has a really nice framework for, you know, you have a process function, you have a setup function. You can put MATLAB code in there and turn it into a VST plugin. So that's nice. In the plugin, there's 3 modes of operation that I've defined: these traverse, semantic, and manual, and I'll talk about that more in a second. And again, the user has control over these 12 different models. They can choose which one they want to listen to, basically. And they all have different representations. And there's some workflow I had to do to get this machine learning model to actually work in the audio toolbox. And like I said, the first thing we do all the training in Python. The workflows and the libraries, in my opinion, are a bit better working in something like Keras or PyTorch, and then transferring to MATLAB or Juice if you want to actually do the implementation. So we save out the weights first. Then I have a MATLAB function that converts these to mat files in the format that my classes they understand. Then, like I said, I also implement the model architecture in pure MATLAB code. So doing the matrix operations of the neural network, I implemented in MATLAB so that they could be compiled into the VST plugin. Then there's also some UI controls that basically control swapping out these weights in real time in the plugin, so that we can have the same exact model architecture, flip the weights, and now we're using a different model, basically. And the final step is basically implementing a 5-band parametric EQ in MATLAB. So this is me just creating 5 biquad filters using the basic, parametric EQ thing. So there's a low shelf, 3 bandpass filters, and the peaking filters, and then a high shelf filter. And so we connect those EQ parameters that the model is predicting directly to those coefficient generations, and then that coefficient generation process. And then we have this plugin running in real time to do the actual EQing, right? And here's what the final EQ plugin looks like with the full-blown interface with all of the elements. And I'll just walk through some of the elements here so we can understand. So in the traverse mode, you'll be doing the latent space traversal that I mentioned. And this is where you have those X, Y, Z controls. And this is kind of the main way you use the plugin to sample. But there's some other modes too. So there's also this semantic mode, which what it does is I've kind of pre-chosen different points in the latent space for each model that I think are warm, bright, or different things like this. And then what you can do is actually sample, interpolate between those 2 points. So you pick 2 points in the space, move between them, and you get some EQ that's somewhere between those two. And you can pick whichever direction you want. That's kind of interesting. In the future, I'd like it so you could have the user pick one point and another point that they want arbitrarily and move between them. But currently wasn't able to implement that with the current MATLAB framework. And finally, there's the manual mode. So you see here the original controls of the EQ. Now, how I envisioned this originally working is that moving the X, Y, Z controls of the plugin would change these knobs in real time. But unfortunately, the MATLAB didn't allow me to do this either. So I'm looking to potentially have this working in a juice version where you would actually be able to see this. And then the idea is you kind of do the coarse control with those XYZ sliders, and when you get very close to the EQ you want, you can tweak a little bit with the manual mode. And then here's where you actually control the model, choosing the latent dimensions, the beta that we talked about, and all of this. And then there's also finally an automatic gain compensation, which helps because since you're changing these EQs so drastically, the overall level can adjust a lot in real time. So this tries to keep the level constant when you're listening, so that you can hear the timbre change more clearly. And also there's a light version, because the whole point of this, right, is to create a simple version for novice users. They don't want to have all this clutter. So the main plugin I just showed was kind of demonstrating all the possibilities, and it was also a way to do the testing ground of listening to different models. So in flowEQ Lite, it's the stripped down interface that's got just these 3 XYZ controls and one model that I picked as the best. And then this is meant towards those novice users that just want to kind of almost look at it like an Instagram filter where you can just move these sliders back and forth until you hear what you're happy with. That's the idea. And also there's a demo of this on YouTube. I won't play it now, but you can check it out if you want to hear the plugin in action and kind of get some more explanation of how it might actually be used. But that kind of concludes everything I want to talk about today. Thank you so much for coming and listening. I encourage you, if you want to know more about the math, like how this works, the implementation details, please check out the project website. Also, all of the code is public available on GitHub, including the Python and the MATLAB code. And there's also additionally, if you don't have MATLAB, you can't build the plugin. I already have builds for Mac OS and Windows 10, so you can also just download those VSTs and try them out as well if you're interested. Thanks again, and hope you enjoyed this.
Wow, thanks a lot, Christian, for that talk. Can you hear us, Christian?
Yes, thank you. Yes, thanks for having me.
Yeah, very interesting. We had a couple questions from the chat. If you could, the first question is: have you explored conditional VAEs in addition to VAEs?
Yes, I didn't include that in this part of the work because there are some challenges with having that be part of the real-time aspect. So something that, like, the obvious idea would, maybe just extract some features from the audio signal that you're trying to process, and then use those features about the audio to condition the VAE, for example. But the problem is you need to then do this feature extraction and additionally make your model bigger, all in real time, if you're trying to process something. So, and then you have this problem where if your signal fluctuates over time, now your EQ conditioning fluctuates over time. So I found that it was kind of just a cleaner way to use just a simple VAE here for the plugin, but I think there could be some interesting applications for the conditional VAE.
Okay. We also have a question. Will it be possible to use a .wave or other audio formats to give the AI algorithm a sample of what an instrument to sounds like, or is it still tweaking the EQ controls?
Yeah, I mean, that's a great question, and I think that's where we would eventually want to go. But the problem is we actually need more data to be able to train a model that would do this kind of thing, and we just don't have data of this kind right now to do something like this, unfortunately. And in my master thesis, I'm actually working on some elements of this. So maybe we will see some results there.
And we have one more question from Anthony Nichols. Given this is part about using ears rather than eyes, were the training samples made by people who switched off the UI originally? People tend to overuse EQ, and it would be a shame if it was.
Yeah, I agree with that sentiment, but our viewpoint is a little bit different here because the data that this was, like the data we're using here was collected in a totally different environment than this environment. And they were specifically targeting professional engineers to collect these. So we kind of are trusting that their choices were good, that the professional engineer isn't being fooled by their eyes, hopefully.
We have another question. This is really interesting talk. I'm not sure if I understand this question. What happens with higher dimensional latent space?
Sure. Yeah, so as you increase the dimensions of the latent space, you get more degrees of freedom. So you then potentially get your latent space can represent more interesting or more complex relationships among the input features. So it means you would get more sliders to control, and you would potentially have more fine-grained control. But the trade-off there is we want to keep this simple. So I chose 1, 2, and 3 because this gives the user a lot of flexibility about how much control they want, and it's also easy to visualize.
Okay. Did you have any user testing for the EQ, and did you get any feedback from them?
Yeah, only informal user testing. I would like to continuing this work would be to do a more formal evaluation of the plugin, but in the limited testing I did, there was some interesting feedback as far as I think the real application for this, like I said, would be in either novice users, like just musicians, people that don't want to get into the nitty gritty, or maybe for some sort of mastering kinds of applications or even when the users, like something cool that someone mentioned was that you could see this being an option on something like Spotify, maybe where you want the users just to be able to adjust the control, but not have to know everything about an EQ, for example.
Great. And we have another question. How does this compare to Sonable Smart EQ?
I can't say that I'm familiar enough with it to compare.
Okay, great. Okay, it looks like that's all the questions from our chat.